to Rohali for part 2 of this morning's presentation.
Thank you, Stacy, so much. So I'm Rohali, and I'm the biostatistician at the Pediatric Biostatistics Core. I'm very happy to be a part of Emory family and present here. So today I'm going to talk about the continuous data analysis and interpretation. So here's an outline for today's lecture. So since Scott has already talked about categorical data analysis, my primary focus would be on continuous outcomes. So I'll be describing continuous data, summarizing continuous data using the measures of location and dispersion, summarizing continuous data using graphs, also a little bit about understanding normal distribution, checking the assumptions of normality, understanding the measures of association as well as interpretation. All right, so what is continuous data? So basically, continuous data can have values on a continuum. It can be measured on a scale or continuum and can take any value within a certain range. So continuous variables can take on any numeric value, it can be meaningfully divided into smaller increments, including fractional as well as decimal values. There are any infinite number of possible values between any two measures. Typically, you measure continuous variables on a scale. Examples include a person's height, it could be any value. So within the range of human heights, not just certain fixed values. Temperature, a child's birth weight, or age of a person, etc. So summary statistics help you in summarizing and providing information about your sample data. So it tells you something about the values in the data set. So this includes where the median lies, whether your data is skewed. So basically, summary statistics fall into three categories: measures of location, also called as the central tendency; measures of spread, also called as dispersion; and graphs or charts. All right, so let us look at the measures of location or central tendency. So the measures of location or central tendency tell you where the data exactly lies and where the trend lies. So the three measures of central tendency are the mean, median, and mode. So I'm sure a lot of you in this room are familiar with how to calculate mean, but I will just quickly go over. So basically, mean is the sum of observations divided by the number of observations. Let's say, and it is specifically the arithmetic mean. Let's say you have a sample of 5 participants with the following age measurements in years: 6, 8, 10, 12, and 14. And you are asked to find the mean. So all you have to do is add all these ages and divide by 5. So you can just try this simple arithmetic calculation and tell me what is the mean. It's 10, correct? So all you have to do is divide these numbers and divide by the add up the numbers and divide by the sum of observations. So which will be 10 years. So the mean here is 10 years. So the second measure of central tendency is the median, and the median is the value. It is a middle value in the series. So here again, we have sample of 5 with age measured in years. In order to find the middle age, all you have to do is look at the middle value. So what is the middle value in this case? 10. So, okay, so yeah, 10. So the median age here is 10 years. Now you may have a question, what to do in a situation where you have like even number of elements, how to find the median. So any guesses? What's the median when you have a situation when you have even number of elements? What is the middle number? Yes. So to find the median, so yeah, the 11 years is the median. So in situations where you have like even data elements, all you have to do is pick the two middle numbers and take the arithmetic mean. So in order to arrange the median, all you have to do is arrange the data from smallest to largest. And then if the number of data points is odd, the median is the middle point in the data. And if the number of data points is even, the median is the average of the two middle data points in the list. Moving on to the third measure of central tendency, which is the mode. And mode is the value that occurs most frequently in the data set. For example, in the data set 244364, since 4 occurs more number of times, it is the mean here. So to find the mean, you need to arrange the data points from smallest to largest and find the number that appears most often. So these are some of the hints to remember the differences between mean, mode, and median. So à la mode is a French word that means fashionable. So it also refers to a popular way of serving ice cream. So mode is the most popular or fashionable member of the data set. So that's how you can remember mode. The mode is also like a word most. How to remember mean? So mean is something that requires you to do like a calculation or a simple arithmetic. So it's a mean one. So that's how you can remember mean. And median has the same number of letters as middle. And also if you're familiar with the glossy median on the road, so that's how you can remember median as well. Okay, so only the measures of central tendency are insufficient to summarize or describe your data. Two data sets can have same mean, but they are entirely different. So thus to describe the data, one also needs to know the extent of variability. So in statistics, the measure of dispersion helps you to interpret the variability of the data. That is to know how much homogeneous or heterogeneous your data is. And in simple terms, to know how squeezed or scattered the data is. So let's look at some of the measures of dispersion. So range, interquartile range, and standard deviation are some of the common measures of dispersion. So range basically tells you how spread out your data is, and it's the difference between the largest and the smallest observation in the data. For example, you have 1, 2, 3, 4, 5, 6, 7. The highest value is 7 and the lowest is 1. So all you have to do is just subtract 7 minus 1 to give you the range, 6 here. And interquartile range is another measure of dispersion. It is just the range of the quartiles. So basically, it's the distance from the largest quartile to the smallest quartile. And all you have to do is subtract Q3 from Q1. Let's see what is Q3 and Q1 and how to obtain that. So quartiles basically are divided into a set of 4. So 50% is the median, which is the quartile 2, which is the middle quartile, as seen in the image. Quartile 3 is the upper quartile on the right side. So in order to find the quartile 3, you have to find the median of the upper half. Quartile 1 is obtained from the lower half of the data, and you have to find the median of the lower half of the data to find the quartile 1. So Q3 minus Q1 will give you the interquartile range. In this case, 77 is the quartile 3 and quartile 1 is 64. You have to subtract those two to get the interquartile range. So to find the interquartile range, you have to order the data from least to greatest, split the data into upper half and lower half, find the Q1, Q3, and subtract Q3 from Q1. All right, so the third measure of dispersion is the standard deviation. It is the most important and commonly used measure of dispersion. So it measures the absolute variability of the dispersion. So the higher the dispersion or variability, the greater is the standard deviation, and greater will be the magnitude of deviation of the value from their mean. And it is also represented by a Greek letter, sigma. So it is a little bit tricky to calculate standard deviation by hand. So usually the statistical software can do a job for you. So however, here are the steps to calculate standard deviation manually. So initially you need to work out the mean and then subtract the mean individually from each of the numbers given and square the result. And then you can add up all these results and divide it by the total n, and finally square that, and then we are done. All right, so you can summarize the continuous data using the graphical approach as well. And the most commonly used graphs for summarizing continuous data are histograms, scatter plots, and box plot. So histograms are a standard way to graph continuous variables because they show the distribution of the values. So the histogram here helps you determine whether the distribution of the body fat percentage values for adolescent girls are symmetric or skewed. So it also helps you in understanding the range of values and identify where the common values fall. Here's a scatter plot. So when you have two continuous variables, you can graph them using a scatter plot. The scatter plot here shows how the body fat percentage tends to increase as BMI increases. Okay, so when you have continuous variables that are divided into groups, you can use a box plot to display the central tendency and spread of each group. For example, fertilizer C here is associated with the highest plant growth, while type B produces the greatest variability. All right, so any questions so far? We are good? Okay, great. Okay, so it is very important to check the distribution of the data in order to decide the type of test you pick to analyze continuous data. So data can be distributed or spread out normally or non-normally, and it can help, it can be spread out more on the left or more on the right, just like the positive skew and negative skew, indicating non-normal distribution. But there are many cases where the data is tends to be around a central value with no bias of left or right, and it gets close to something called as normal distribution to the first picture there. So let's see what you mean exactly by positive and negative skewed distributions and the normal distribution. So a positively skewed distribution means that it has a long tail in the positive direction, a long right tail, as you can see over there. For a positively skewed distribution, the mode is less than the median, which is less than the mean. So basically, in a positively skewed distribution, there are large positive outliers, which is why the mean tends to be pulled towards upward. While a negatively skewed distribution has a long tail in the negative direction, so a long left tail. For the negatively skewed distribution, the mean is less than the median, which is less than the mode. In this case, the large negative outliers tend to pull the mean downward, as in the pictures displayed over there. Okay, so coming to normal distribution, there are three things that should come into your mind when you think of the word normal distribution. The first thing is the bell-shaped curve. So as you can see here, basically this looks like this is a bell-shaped curve. That means that the mean is sitting right in the center, and most of the data that's sitting around it on either side of the mean. So I'll talk a little bit about it later, but here how a bell-shaped curve looks like. The second thing that should come into your mind when you think about normal distribution is that the total area under the curve is equal to 1. So all of this area underneath this bell-shaped curve, all of it from the tails, all of these, the area is 1. So the third thing that you should think of when you think of a normal distribution curve is that the bell-shaped curve is symmetric in nature. So the half of the picture here is 0.5 and half of the picture is 0.5. So all of that area is symmetric in nature. So those are the three things that you should think of when you think of a normal distribution. Let me go a step forward and introduce you to the standard normal distribution. So standard normal distribution is all these three things plus the Greek letter population mean, which is in the center, that is equal to 0, and the population standard deviation, sigma, that is equal to 1. So these are the 5 things that constitute of standard normal distribution. These are some of the examples of normally distributed data, such as heights of people, size of things produced by machines, errors in measurements, blood pressure, marks on a test, etc. So when your data is normally distributed, the best measure of central tendency to describe your data is reporting the mean and standard deviation. Also, parametric tests are your go-to test for measures of association when your data is normally distributed. And I'm going to talk a little bit about a parametric test moving forward. All right, so non-normal data distributions are very common in research studies, primarily because we cannot control how the outcomes will result. Variables such as cost, length of stay, duration of mechanical ventilation, weight, lab values, etc., are all normally distributed. So when you are in doubt whether your data follows a normal distribution, it is always safe to go for a non-parametric test. They are very conservative estimate, and however, they are most powerful if the data is truly non-normal. So if after looking at the distributions of the data, you find that it is skewed, you would have a couple of options, but reporting the median and its interquartile range is the most common one. You can also sometimes transform the data, such as do like log of the values, and if you're finding a logarithmic distribution of data. When you have skewed data, you can always use non-parametric tests, such as the Wilcoxon rank sum test, which is a non-parametric alternative to two-samples t-test. Wilcoxon sign rank test, which is a non-parametric alternative to paired t-test, and Kruskal-Wallis test, which is a non-parametric alternative to one-way ANOVA. So this is a Halloween week, and in between, all the tricks and treats, we data geeks are chuckling over this cute meme over the social media. So here's a little ghost humor for you all. I hope you all understand when you come across this meme. All right. So, okay. So in order to check if your data follows normal distribution or not, we need to assess the data for normality. So assessing normality is not only relevant for determining the nature of distribution, but also is a prerequisite for many statistical tests, because normality is an underlying assumption in parametric testing. So there are two main methods of assessing normality. One is the graphical, the other is the numerical method, including the statistical tests. So the most commonly used graphical methods to assess normality include the QQ plot, box plot, and the histogram. So the normal QQ plot, here's the output from the normal QQ plot. So if the data points are normally distributed, then the data point, if the data points are normally distributed, then the data will be close to the diagonal line in this situation, just like that. So if the data points stray away from the line in an obvious nonlinear fashion, then the data are not normally distributed. So as we can see from the normal QQ plot here, since the data points lie close to the diagonal, the data is normally distributed. Coming to the box plot, so box plot is another way to assess the normality of the data. So it shows the median as a horizontal line inside the box, and the interquartile range as the length of the box. The whiskers, that is the line extending from the top as well as the bottom, represent the minimum and the maximum. So a box plot that is symmetric with the median, the line that is approximately in the center, and with symmetric whiskers indicate that the data have come from a normal distribution. The third one is the histogram. So histogram is basically an estimate of the probability distribution of a continuous variable. So if the graph is approximately bell-shaped and symmetrical around the mean, we can assume that the data is normally distributed. So if you're all unsure of being able to correctly interpret the graph, rely on the numerical method instead of the graphical one, because it can take a fair bit of experience to correctly judge the normality of data based on the plots. So graphical method of testing normality is suitable for initial judgment, but it is not exactly reliable. So visually, it can be identified that the bell shape is formed, or observed value is close to normal distribution, but actually the results cannot be generated. Furthermore, this method is not really suitable for large sample sizes. So therefore, it is important to conduct the empirical test of normality using the statistical software. So the null hypothesis to test the assumption of normality is that the values are sampled from a population that follow a normal distribution, versus the alternative that says the values are not sampled from a population that follow a normal distribution. So there are different tests to check for the assumption of normality, but the most common tests are the Shapirov-Wilk and the Kolmogorov-Smirnov test. So the table presents the results from the well-known test of normality, namely the Kolmogorov-Smirnov and the Shapirov-Wilk. So the Shapirov-Wilk test is more appropriate for sample sizes which are less than 50, but sometimes they can also handle sample sizes up to 2,000. For this reason, we will use the output from the Shapirov-Wilk test. So we can see from the table that the beginner, intermediate, and advanced scores group and the dependent variable time was normally distributed. And how can you say that? So if you look at the the significant value under the Shapiro-Wilk on the right corner, you can see that all of those values are greater than 0.05, which indicate that the data is normal. So if it is below 0.05, then it means that this data significantly deviates from the normal distribution. Okay, so now let's discuss different measures of associations used in continuous data analysis. So based on the discussion of the data, you decide which test to perform. So if your data is like normally distributed, you perform a parametric test, and if your data is non-normally distributed, you perform the non-parametric test. So the different parametric tests are the two sample t-test, paired t-test, one-way ANOVA, and the non-parametric tests are the Mann-Whitney U-test, Kruskal-Wallis test, and the Wilcoxon-Saint-Rank test. So basically, two sample t-tests are probably the method you are used to seeing for continuous data, in which the null hypothesis is that the population means of two groups are equal versus the population means of the two groups are not equal. So in this type of statistical testing, the data must be normally distributed, such as in the bell-shaped curve, and the groups should have equal variance. You can determine this by something called as Levene's test, in which if it is true, then there are equal variances, and if it is not, then there are not unequal variances. And the variance factor can help you determine whether or not this test can be appropriate between your groups. So for the two sample t-test, it is possible to interpret it as one-sided or two-sided. The most common is two-sided, in which a direction is not specified when talking about the alternate hypothesis. They are just different. So one-sided, in contrast, is when you do specify the direction. Either one group is less than or greater than the other group in terms of variable measures. So these have like smaller p-values, half as much as the normal ones, and are used in things like superiority, non-inferiority, and non-equivalence trials. Outside of those kinds of designs, be super cautious of someone reporting the results of one-sided test without any major justification. So when to use a t-test? So t-test assumes that your data are independent, whereas for paired t-tests, which we're going to talk about later, your data should be dependent. Your data are approximately normally distributed and have a similar amount of variance within each group being compared, which is the test for homogeneity of variance, or the Levene's test. So you report the results of a two-sample t-test in this way. So you need to report the means of both the samples, the type of t-test you conducted with, the type of t-test, whether it is two-sample t-test or paired t-test, and whether it is one-sided versus two-sided, the value of the t-statistic, as well as the degree of freedom and the p-value. So t-tests are like very difficult to compute by hand when you have large samples. So usually the statistical software does the job. How many of you use GraphPad here? Have you ever used GraphPad? Have you? Yeah, it's easy, right? It's easy to compute t-test and like all sorts of different tests using GraphPad. So maybe you can like try exploring, right? So this is a template for interpretation of two-sample t-tests that you can use later. So I'm gonna just go through it. So data are a mean and plus or minus standard deviation. That's how you usually report, unless otherwise stated. So there were 20 male and 20 female participants, and the two-sample t-test was run to determine if there were differences in engagement to an advertisement between males and females. So how we interpreted the results. So the advertisement was more engaging to male viewers. So you put the mean and the standard deviation within parentheses than the female viewers, the mean and standard deviation of female viewers, and a statistically significant difference of 0.26. That is, whether the difference was found or not. And then the 95% confidence interval. You present the t-statistic, and within the bracket, you present the degrees of freedom. and then the p-value. You can rephrase it according to the significant value as possible. All right. So moving on to the other set of measure of association that we can often encounter is the paired data. So the paired samples t-test can be used to analyze the differences between conditions or differences between time points. For example, in the pre-post study design, which is very common in medical research. So this is done when the subject is measured twice. These samples are not independent because they utilize the same subject for two different measurements in the data set. And because of this, we must account for the correlation when we are running statistical analysis. So this test has a null hypothesis that addresses whether the mean differences between pairs of measurements is 0 or not. So MD here is the mean difference. So if there are any differences between the first observed and the second observed mean, 0 or not, that's how you test it. So on the right side, you see pre and post. So you'll have to subtract pre from post, and then you get the difference. So 20 minus 10 is 10, 30 minus 21 is 9, and so on. Look at the mean difference for pre and post and see whether that is equal to 0 or not. So this is a template for interpretation of paired t-test. So a paired t-test was used to determine whether there was a statistically significant mean difference between the distance ran when participants imbibed a carbohydrate protein drink compared to a carbohydrate only drink. Data are mean and standard deviation presented as mean plus or minus standard deviation unless otherwise stated. Participants ran further when imbibing the carbohydrate protein drink as opposed to the carbohydrate only drink. So here they are same participants but different conditions. The statistically significant increase of 0.136 was found. And then again, we present the t-statistic and the degrees of freedom and the significance level. And again, you can rephrase it according to the whether the results are statistically significant or not. Okay, so t-tests themselves are useful tools, but they only work when you have want to compare two groups. So what do you do in a situation where you have more than two groups? So we use something called as the analysis of variance, or ANOVA. So for the analysis of variance, the null hypothesis is that all groups are equal to each other, and the alternate is that not all the group means are equal. So the ANOVA utilizes an omnibus test for any differences between groups, and it uses the F distribution, and a less than 0.05 implies that some means are different from other. However, it does not imply which ones are. So in order to find out that, we would need to do like post hoc multiple comparisons to define which groups are significantly different from other. So when to use one-way ANOVA? So one-way ANOVA assumes that your data are independent, are approximately normally distributed, and have a similar amount of variance within each group being compared, also known as the homogeneity of variance, or you can do the test of Levene's test to find out that. So post hoc test. So basically ANOVA tells you that there are differences among the levels of independent group, but won't tell you where the difference is, like where the significant difference lies. So in order to find how the treatment levels differ from one another, we perform the post hoc comparisons. So the different post hoc comparison techniques available are the Tukey-Kramer, Dunitz, Bonferroni, Schiffe, Hom, etc. So in all of this test, there is a specific p-value that looks at the pairwise comparisons. So you can look at the specific differences between two particular groups. For instance, in this infographic, we are comparing the mean and comparing if the mean is different between group A and B, B and C, and C and D. So always be cautious. Be cautious of the number of pairwise comparisons this infographic has presented. So this infographic only shows 3 different comparisons in the 4 groups, but in actuality, there is a possibility of 6 comparisons in total. So the multiple comparison results will also compare between A and C, A and D, as well as between B and D. So that way you can determine where exactly the mean significant difference lies. Okay, so reporting the results of the mean. So just like the t-test, all you have to do is report the means of all the samples you have in the data set, the test name, the value of the F statistic, the degrees of freedom. Remember that there are 2 degrees of freedom for ANOVA. One is the degrees of freedom for between subject and one is within subject. And then the p-value. So let's look at the interpretation of one-way ANOVA. So one-way ANOVA was conducted to determine if the ability to cope with workplace-related stress was different for groups with different physical activity levels. So participants were classified into 4 groups: sedentary, low, moderate, and high levels of physical activity. And the cope with workplace-related stress scores was found to be statistically significant, different between different physical activity groups. And the F statistic is presented here, as well as the 2 degrees of freedom with the significant p-value. CWWS scores increased from the sedentary to the low, to moderate, and to high physical activity groups. So we know that these scores are different between different physical activity groups like sedentary, low, and moderate, but we don't exactly know where this difference lies. So in order for that, we need to do the multiple comparison test. And here we prefer Tukey. So Tukey post-hoc analysis revealed that the mean increase from sedentary to moderate was found to be statistically significant, as well as the increase from sedentary to high was found to be statistically significant, but no other group differences were found to be statistically significant. So you can always use this as a template for your future reference. All right, so coming to the non-parametric test. So non-parametric test that you would use for non-normal data does not assume certain distributions. So basically, in this situation, the data is ranked in, and the ranking is utilized in performing the test. So the infographic on the right shows the 3 non-parametric tests that we should run instead of the particular data if the continuous variables are non-normally distributed. So the non-parametric alternative for 2-sample t-test is the Wilcoxon rank sum test, also called as the Mann-Whitney U test. For one-way ANOVA is the Kruskal-Wallis test, and for the paired t-test is the Wilcoxon signed rank test. So these are more labor intensive to calculate by hand. For computer calculation, of course, this isn't an issue. So let's look at some of the non-parametric tests. So Mann-Whitney U test is the most popular non-parametric test to compare outcomes between 2 independent groups. So the null hypothesis to conduct Mann-Whitney U test is that the 2 populations are equal versus the 2 populations are not equal. The procedure for the test involves pooling of the observations from the 2 samples into one combined sample, keeping track of which sample each observation comes from, and then ranking the ranks from the lowest to highest. So the interpretation for Mann-Whitney U test is that the Mann-Whitney U test was run to determine if there were differences in engagement scores between males and females. Median engagement score was statistically significantly higher in males than in females. And then you present the Mann-Whitney U test statistic, the z-score, and the p-value, which is obtained from your output. So Wilcoxon sign rank test is the another popular non-parametric alternative, and it is used to determine whether there is a median difference between paired or matched observations. So this test can be considered as a non-parametric alternative to the paired samples t-test. The Wilcoxon rank test tests the null hypothesis that the median differences between 2 related groups is 0 in the population, right? So this is the interpretation. So a Wilcoxon sign rank test was conducted to determine the effect of exercise on C-reactive protein. So 10 participants were recruited to a study who each underwent a 6-month exercise training program. CRP concentration was measured pre-intervention and then immediately post-intervention. And the results that we found are presented here. So of the 10 participants recruited to the study, the exercise training program elicited a decrease in CRP concentration in 9 participants post-intervention, whereas 1 participant's CRP concentration increased post-intervention. So there was a statistically significant median decrease in CRP concentration from a pre-intervention to post-intervention. And then you present the z-statistic, z-score, and the p-value here. Kruskal-Wallis is another popular non-parametric test to compare outcomes among more than two independent groups, which is an alternative to a one-way analysis of variance. The null hypothesis here is that the K population medians are equal versus the K population medians are not equal. So I have indicated K here because you can have any number of groups, more than two groups basically. So the procedure for the test involves pooling the observations from the K samples into one combined sample. So keeping track of which sample each observation comes from, and then ranking the sample from lowest to highest, that is from 1 to n. So how you interpret your results will depend on whether the distribution of scores for each group of the independent variable had the same shape, which is one of the critical assumptions of Kruskal-Wallis. If the distributions are similarly shaped, you can use the output to compare the medians of your dependent variable. Whereas if your distributions have different shapes, you can use Kruskal-Wallis H-test to compare the mean ranks. So here, a Kruskal-Wallis test was conducted to determine if there were differences in coping from work-related stress scores between groups that differed in their level of physical activity. So there were three groups: sedentary, low, moderate, high physical activity level groups. So the results that we found are presented here. So the median CWWS scores were statistically significantly different between the different levels of physical activities, and the chi-square statistic, the degrees of freedom, the p-value is presented here. Subsequently, pairwise comparisons were performed because there were statistically significant difference between the three groups. And in order to find where the difference lies, we would perform the post hoc test, and we used Dunn's procedure here. And a Bonferroni correction for multiple comparisons was made with statistical significance accepted at p less than 0.0083. So the post hoc analysis revealed statistically significant differences in CWW scores between the sedentary and moderately and sedentary and high physical activity groups, but no other groups were found to be group combinations were found to be significantly different. So here's a summary of the test to be used based on the type of analysis. So we can quickly go over this. So for the analysis type here, if you want to compare the means between two distinct or independent groups, for example, is the mean systolic blood pressure at baseline for patients assigned to placebo different from the mean for patients assigned to the treatment groups? Since you're comparing the means between two groups, you can prefer the two sample t-test in case your data is normally distributed. If not, the parametric alternative is the Wilcoxon rank sum test. The second situation here, we are comparing two quantitative measurements taken from the same individual. And the question is, was there a significant change in systolic blood pressure between baseline and the 6-month follow-up measurement in the treatment group? So since the measurements are coming from the same set of population, but in different conditions at different time points, we use the paired t-test when your data is normally distributed, and the non-parametric alternative when your data is non-normally distributed is the Wilcoxon sign rank test. The third situation is when you're comparing means between 3 or more distinct or independent groups. So if our experiment had 3 groups, that is placebo, new drug 1, and new drug 2, we might want to know whether the mean systolic blood pressure at the baseline differed among the 3 groups. So in that situation, when you have a normally distributed data, you can prefer one-way ANOVA or analysis of variance, which is your parametric test. And when it is non-normally distributed, you can prefer the non-parametric alternative, which is the Kruskal-Wallis test. So now that we have covered all of the tests, I thought it would be helpful if we look at the real-life example of a table from a journal. So in these tables, you are able to decipher what kind of tests were run on the variables on the left side based on the results reported. For instance, we see that age is reported as the median and interquartile range. So what can you say if you report median and interquartile range, whether your data is normally distributed or non-normally distributed? Non-normally, correct? Right. So for instance, when the age here, the age is reported as median or interquartile range because the data was non-normally distributed, and since that was the case, we can say that the measure of association here was the Wilcoxon rank sum test to look at the differences between the two groups. For the variable of sex here, which is a categorical and a binary variable, the proportion of male to female is reported. So we know that we would need to run a chi-square test of distribution here across these categories. Lastly, we look at the past variable, the last one, that is reported as the mean and standard deviation. So we know that the p-value are derived from comparing the two means in a two sample t-test. All right, so here's a cheat sheet for you for your quick reference. I know that this is a lot, and probably after you leave this room, everything must be saturated. So I'm leaving a quick cheat sheet for you to go over for your future reference. So it lets you pick the type of test given the number of groups, whether your data is paired or independent, whether the equality of variance of your test is true or not, and what kind of, based on the distribution, you can pick the test. However, in case if you have any question about the test, you should use, in order to look at your data, always feel free to consult your statistician or the core that I work for. And then we can help you explicitly understand the distribution of your data and the type of test to pick. So here are the links for some excellent resources for anyone interested in learning statistics in detail. Both of these resources feature fun as well as interactive learning modules, such as web applications, statistical textbooks, codes. So it would be really nice for someone to start off, especially for beginners. All right, so now that we have kind of wrapped up and covered both categorical as well as continuous measures of association data. So one of the resource that you have as long as you are in your fellowship is the in pediatrics, which I believe all of you are. So is the utilization of my group, where Scott and I both work for, is the pediatric biostatistics core. Here's the link attached. I'm sure many of you would require this link, and you can access this link and get to know what kind of services we offer throughout your fellowship, and consultation, and whatever help with your research project is, we can help you with. So you can just explore this link here and reach out to us in case you have any questions in future. All right, that's all for now. And yeah, I'm ready to take questions if you have any. This one? So basically, when usually when the data is not normally distributed, we report the medians and interquartile range, because when you say the data is not normally distributed, it means your observations are skewed either to the left or right. So it means that you have a lot of outliers in your data, and in such situations, mean is very sensitive. And is not a good representative of central tendency. So median is not sensitive to outliers, and in situations where you have skewed data, we usually report median as a measure of central tendency along with interquartile range. Any other questions? All right, thank you.